before I forget. So when you're doing regression predictions, so they have predicted a 2,000 square feet house exactly the way we did. I mean, if the answer is 317.85. Remember this slide over here. You can make predictions only between the x values that you have in your sample. You should not do out of sample. Do not try to extrapolate. Go outside your sample and take a house that is beyond your actual size in your sample and take a 900 square foot house or a 3,000 square foot house. That would not be right. Your confidence level is within the range of x's that you have. So I'll talk about the confidence level in a minute, but before that, remember this: while predictions are done, you will have a question or two in your homework which will say, well, can you predict, for this example, for example, the house price, 3,000 square foot house? You should say, no, we should not do that out of sample. The next thing is, what is my regression line then doing? How useful it is, all right? So to determine that, we need a measure, we need a statistic for measuring how good is my regression model. So going back to this, the plot we had, this is house prices in thousands of dollars. All right, and this is square footage. I have all these actual sample values, and then I have the predictions, which is the best line of fit, like so. So this is what we have gained. We have gotten a predicted y hat, which is beta 0 plus predicted beta 1 times different x's, right? Is that a good measure? Is that giving me something good enough? Well, the data is the right answer. I mean, we have to go to the data to answer that. So let's assume I didn't have any excess, all right? And we have done a lot of that kind of example. You just have your house prices. In that data that we were using, all you have is one column, house prices. What would be your best bet of drawing another house? What is the price? How do you predict that? So I say, well, I have for Peachtree City, Centennial area, where I live, the house prices that were sold in the last 10 years are here, or last 1 year. What is going to be the price of the next house sold? What will be your best guess of that? Given all the information I just said. The average, right? That is the best thing we've done. It's the average. We work off of the average. So if we didn't have any square footage of the houses, we'll get the average value of the houses. So these are the different values of the house prices. And let me use a green line to show maybe this is the average y value. All my greens are doing pretty bad. This is the y bar from my sample, right? So we can call this, what did he say? This is the y bar. Yes, sample is right language. Y bar, x bar is the mean value. That is my best guess of what the house is going to be. So if I have to kind of make a measure of what my regression is actually achieving by doing all these mathematics in the background or running this Excel, whatever we did, we need to say, well, if I just didn't have any x's, what would be the errors? Right? We will get the errors for that too. I mean, the difference between the green line and all these blue dots is what the errors would be in that case, right? These are the errors. Question is that my orange line, is it improving on the green errors from what I would have from the orange line? All right? Is the errors from my fitted line better than what I would have without no x's at all? All right, that is the measure we do. So to do that, we make a measure called the total sum of errors, which is called the sum of squared, what do they call it here? Total sum of squares, that's right. Sum squared total is nothing but for each one of these y's, for each one of these blue dots that I have, you take the actual y minus the y bar that you calculated from the sample, and you'll square that and sum that. All right? That is your total sum of squares. Basically, that is your total errors if you use just the mean of y without explaining anything from any x's. Now that you have your x's, and I'll erase the green line, or maybe it's better if I do it from here. So the y bar is actually over here for this in this graph. My green line is the red line for the one on the board. So the total sum of squared SST is what each point, the actual point of y, how far it is from the y bar. If you sum all of that, you get the sum of total squares. Sum of squared totals. All right. Now we move from something which was our best guess when we didn't have any x's. Now we say, well, we'll do a regression. We have the x's, which I think makes sense. The square footage for house prices. And I get the line of best fit from my regression from Excel, and I got that blue line now. So what the blue line does, it gives me a little bit of a different prediction of what, for each of the x's, it gives me a predicted value which is different from the y bar, right? For that x bar, I mean, if I didn't have any x bar at all, I mean, the only prediction I had was y bar. But for that x1, now my predicted value is up there on the line, blue line, right? So that is my explained part. So sum of error which is explained, the abbreviation is a little bit. So regression sum of squared is SSR, okay. The regression sum of squared is what I can explain. So going from that red line to the blue dot line over there for that particular xi is what my regression achieved. So for any of the x's, if I, for this x, the y bar was the best. But in this case, my orange line, it has a little bit better. So this is what my sum of squared regression. My regression is increasing the explanation of how much I can explain of the total variance of y. All right? So that's called the sum of squared regression. So now I have the predicted value minus the y bar, which is my first guess, is the sum of regressions. That's how much I've gained. Whatever then remains is the sum of the residual square. All right? So that's called sum of squared errors, SSE, sum of squared errors or sum of squared residuals of my regression. What is that? It is this residual that we calculated in Excel, remember? It's over here. It's also plotted as residuals here, or if you look at the thing we plotted, the columns, well, this is what my predicted values are, this is the residuals. So if I square the residuals, the errors, I get the sum of squared errors. If I square each one of them and sum it, I get the sum of squared errors. And the predicted value minus the average y is the sum of squared, regression sum of squared. So, relative to, we will see how much the regression is actually explaining different stuff. So relative to the total sum of squares, when we didn't have any x's or any explanatory variables, no x. No x is this, right? How much is my predicted regression explaining better of this whole sum of squared total is what is the measure of my regression. So the more I can explain this, of the difference, if I can, my regression can explain this, the less my error sum, so sum of squared errors will be smaller. The less the errors, the better my regression. My X is actually explaining the real world of Y traces, right? So the smaller my errors after the prediction, the better the regression. So how do you explain that? Well, in mathematical doing this, if you divide the sum of square regressions by the total sum of squares, you get what is called the R squared term. So sum of squared of the regression divided by the total sum of squares is what we call the R squared. That tells you exactly how much of the part that we could never guess with just the average Y that is being explained by the regression. All right? So so if we have a fit like this, that you have, what is the R squared? It's going to be 1, because I told you a lot. There is a little understanding that goes behind what I just said. So think through this. We'll go back and revisit this question again, but see if you can answer this. Why is that R squared 1 in both these cases?
Because it's squared, you can't go negative.
All right, let me say this. That R squared value can be, the R squared can only be, it can never go negative, it's squared. It can range between 0 to 1. So why is it 1 in this case? So what is R squared? R squared is how much by regression the X is explaining the variation of the Y, right? So the regression sum of squared is explaining the total variation of the Y. How much of the predicted value is actually explaining the real Y, right? So when will it be 1? When it completely explains all the Y, right? When there is no residual, when the sum of squared errors is 0, that is when R squared is going to be 1. That means the only time you're going to see an R squared as 1 is if all the blue dots were on this predicted line, right? Which is the case over here. So your predicted line plots each of the actual points on it. There is no residual, all right? If that is the case, then R squared is 1. So 1 is the gold standard, all right? Do you ever get 1 in the real world? Highly unlikely. There is, randomness is part of human nature. So if you're doing any human study, randomness is part of nature in the real world, biological world too. In any statistical world, there is randomness. So R squared as 1 would never, if you're getting R squared as 1, you need to go back and check what sampling you did. Maybe you did something wrong.